All right, this is for the chi-square goodness of fit test. The example I'm going to pull is from your notes. It's the one with 5 categories that compared data from the census based on an age distribution and the distribution of people that answered a landline telephone survey. You're going to find the goodness of fit is a relatively basic test to do, but the only thing extra to just run the test is you go to stat and edit, and you have to enter your counts, which if you think about is kind of like, well, yeah, I mean, that's really the one thing the calculator is going to need to do the test. Every test we've done has that to some extent, where there's some type of data or some kind of measurements about our data that the calculator needs. Okay, you can see here, observed in 1, expected in 2. That's always the case with the goodness of fit. And make sure that they match up. Okay, so the 141 and the 200.17, those go together because that's the observed and the expected count for people in their 20s. Okay, 30s, 40s, 50s, and 60 plus down at the bottom. Once you're good with that, we're over to stat test, and it's way down at the bottom. You're looking for chi-squared GOF, which is short for goodness of fit. Okay, notice there's 2 chi-squared tests. For the goodness of fit, you obviously want the GOF. That's the one you're after. And then just double check. Observed is in 1. If it wasn't, you could hit second 1. That would switch whatever is there to list 1. And then second 2 would switch the expected over to 2. Degrees of freedom, that should be 4. Categories -1. That all looks good. And then we hit calculate. So in your do step, the first 3 things you would have. You'd obviously want the chi-squared value, the p-value, and the degrees of freedom. With the chi-squared value, remember that as far as showing work, we show 2 contributions. Okay, so in your notes, I showed you the whole like observe minus expected squared over expected. We did that for people in their 20s and in their 30s. And then we just said dot, 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 and then equals the chi-squared value. One other thing that you have here is if you scroll to the left or right, you'll see this 17. So there's 5 contributions to the chi-squared value. These are not needed in a 4-step, okay? Because the contributions would kind of tell you where the bulk of that chi-squared value is coming from. And in just a regular 4-step for a goodness of fit test, the conclusion does not get into that. We would, with this p-value, we would reject HO and say that we were convinced that the distribution of ages who answered a landline survey and the actual age distribution are not the same. And that's all we say. We're convinced that they're not the same. If a follow-up question got into which category is kind of giving us the biggest difference, you could look at the contributions. Okay, so right away, 17.49, that's 20s. Keep scrolling along. 6.8, roughly, of the chi-squared value came from people in their 30s. So that was a little bit, not as much as the 20s. Check out 40s, 0.037. That was one where the observed and the expected were almost the same. So really, the 20s, people in their 20s is way off. 30s a little bit. 40s not so much. That one's pretty much on. 50s. Once again, 50s is a big issue. 14 of the chi-square value of 48 is coming from people in their 50s. And I think 60s was quite a bit off too. Not as much as 50s, but about 9.2. So really 4 of the 5 were pretty significant contributors to the chi-squared value and only people in their 40s. weren't. But again, that's there if a follow-up question asks you. Okay. You don't, I mean, if you're just doing a 4-step, you can disregard the contributions and you just need the chi-squared value, the p-value, and then the degrees of freedom.